Good morning, class. Today we are entering Chapter 5, and Chapter 5 deals with what we call relationships about triangles, or relationships within triangles. The first part is mainly about introducing different shapes that are in triangles that we have previously not talked about, like midsegments, perpendicular bisectors, and so forth. And then the next part will be what their centers are and different shapes that are formed, or different parts of a triangle that are formed by these other parts. And then we finally finish up with inequalities in a triangle. There's a lot of inequalities, however, they're useful to us. The first thing that we'll be focusing on will be the Midsegment Theorem and a coordinate proof. This is a 2-day section usually, partially because it's the day we come back and from break, and that's usually why it was a 2-day section. And also coordinate proof can be somewhat difficult at times. Alright, the first concept that we have today will be the definition of midsegment. What is a midsegment? And that's pretty straightforward. If I think of mid and segment, it's a middle segment. It connects two midpoints of a triangle. So if I look right here, the midpoint of this side of this triangle and the midpoint of this side of this triangle are connected by this segment right here. This here is definitely a midsegment. However, if I look over here, this shape, even though it looks almost identical to this one, in fact I think I even copied and pasted, I cannot conclude it as a midsegment because I don't know if it connects the midpoints. Now if it connects this midpoint to this midpoint, midsegment. If it doesn't, I can't say. So here, because it cuts into two congruent parts on each side, midsegment. I didn't really give you an example of concept 1 because generally you can look at it and tell me, is it a midsegment, is it not, does it connect the midpoints? So for instance, just by looking at this diagram, can I tell that segment BE is midsegment? Well, yeah, it connects two midpoints. This midsegment theorem, what it says is the midsegment, the segment connecting the midpoints of two sides of a triangle, a midsegment is parallel to the third side and is half as long as that side. So for instance, right here, this midsegment here, it has to be parallel to this side and it has to be half its length. Always. This is always true. This is something that we can eventually prove. However, I'm not going to prove it right now. But this midsegment is half the length over here and it's always parallel. So if segment BE is a midsegment of a triangle ACD, then segment BE is half the length of segment CD. So this is half the length of this over here. And it's also parallel. The first example that we'll be doing here is just a few straightforward ones. Find the value of x. So I'm given all these different triangles. The first step would always be copy it down. Now I realize they're all labeled with A, B, C, D, and E. However, that's really not necessary for this problem. Each of these, what I need to know is that segment BE is a midsegment. Yep, it is. It cuts this perfectly in half on both sides. Midsegment. 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 Alright, so now that I'm dealing with all midsegments, this is pretty straightforward. Let's show some work. For the first problem over here, what I see is that I have a midsegment right here. And I know that this segment here is half the length of this one over here. There's two ways to do this, and the way that I find easiest is to say this length over here is double this one over here. So x equals 2 times 6. This is arguably the easier way to go about this, is to say that the side over here is twice its length of its midsegment. So if I look, x is 12. That's all they wanted for this first problem. Using the same idea over here, I have two options again. I can say 16 equals 2 times 4x. Again, this length is double that length. So I can get 16 equals 8x, and x equals 2. Distribute 2 times 4 is 8. Divide both sides by 8, I get x to be 2. There is another way to go about this problem. I think you can sometimes run into a little bit of difficulty, plus sometimes you get fractions going this way. But I could have said 4x equals half of 16. That's a true statement. This here is half of this length. And if I then simplify, I get 4x equals 8. Divide both sides by 4, I still get x to be 2. I get the same answer either way. I just like this one because I'd rather multiply by 2 than multiply by a half. But it's saying the same thing. This length is double that length, or this length is half that length. It's just depending on your perspective. The last problem here, it might look difficult. But again, if I'm just using this method here, what I look at is this bottom length has to be double that length. So x plus 4 has to be double x minus 4. Make sure you include parentheses, otherwise you get a wrong answer. So I get x plus 4 equals 2x minus 8. Add 8 to both sides, I get x plus 12 equals 2x. Subtract x from both sides, I get x to be 12. And if I plug this in, 12 plus 4 is 16, 12 minus 4 is 8, and that is half or double depending on your perspective. So here we go. It's pretty much this straightforward. Take the side up, the third side, and set it equal to double the midsegment. I find that to be easier than this method over here. Anytime you see me using midsegments, I'll be using this one here because it's easier. Mathematically speaking, because you don't get a fraction. Alright, so far we've used pretty much the same triangle over and over and over again. However, this is not the only midsegment in a triangle. There's actually 3 of them. This reminds me of something from Zelda, the Triforce. But that's the shape that you sort of get when you have all 3 midsegments. It makes a shape like this. It makes another triangle within this big triangle. I haven't changed anything up here. It's in fact the same exact theorem. However, this here just is showing that there's 3 of them. And the relationship is true for all of them. If BE is the midsegment, which it is, connecting 2 midpoints, it's half the length of this big side, and it also has to be parallel. That's also true for segment BF. However, the side I'm talking about now is AD. It's going to be half the length of this side. And it's also going to be parallel. So basically, the side the midsegment is parallel to, it's half the length of. Alright, so this is the next example you should be able to do. What lengths are equal in the diagram, and which segments are parallel? Well, if I know that segment BE is half the length of segment CD, and I know that this segment here, CF, and segment FD are congruent, well, doesn't that mean segment CF, segment FD, and segment BE are all congruent? Yeah, it does. If this is half the length, segment BE is half the length of this one, and segment CF is half the length of segment CD, well, then they all have to be the same length. The next thing, segment BF is half the length of segment AD. So again, segment BF, segment ED, and segment AE are all congruent. And last but not least, segment EF, segment AB, and segment BC all have to be congruent. Same reason. So their lengths would of course be equal. Parallel. Segment BE and segment CD have to be parallel. Segment BF and segment AD have to be parallel, and segment EF and AC have to be parallel. And here's just it written out in form. Because I asked what lengths are equal, I wrote length of segment BE equals length of segment CF, which equals length of segment FD. But this over here, I said segment BE is parallel to segment CD.